Application of Mohr integral method to determine the displacements of nodes. This is article number 3.7 from the book Mechanical Systems Calculations of the Marine Facilities. Application of Mohr integral. Here we have on the slide the equation of Mohr integral. So the displacement is a definite I-direction number. Under the action of the efforts acting on the mechanical system, we can consider by use of Mohr integral for the elastic system, proportional elastic system. And in general approach, Mohr integral, we can indicate consisting into three summands for the flat state. For the state special in the space, we can consider Mohr integral consisting of 6 summands. It depends on number of the directional ons in the space and on the plane. So the Mohr integral consists of 3 summands in considered case, and the first summand is a total of integrals. Integral and integrand is the fraction of in the numerator we have the product of diagrams of the bending moment. So bending moment of the external force action on the mechanical system and the moments and diagram. And this is a diagram of moments of the unit force action in the direction we would like to find the displacement in which. It's not so much important the sequence of the multiplication in the numerator, because the first can be mi, so the diagram of the bending moment of the bending moments of the frame or any other mechanical system and the influence of unit force, and it can multiply it onto the diagram of moment of the external load. Yes, because we have to assume the property of the reciprocity of the displacements or the elastic, proportionally elastic mechanical systems. The displacement in each direction under influence of force is applied in other directions equal to displacement in other directions under influence of same forces applied to the first one direction. So we have reciprocity of the displacement. So the second summand, we have the displacement and action of the shearing forces. The first one under the bending moments. The shearing forces in the denominator of the first integrand, we have the product of the elasticity modulus E by the moment of the initial of the transverse section of the element of the mechanical system, bended end element of the mechanical system. So second summand is total of integrals, and the integrands are the product of definite factor. We say mu. Mu is a Greek factor. Next we will a little bit explain what is mu. It depends on the pattern of the distribution of the shearing stresses in the transverse section of the element of the mechanical system. And next it multiplied by the fraction. Fraction is in the numerator, the product of the shearing force diagram Q of the external load by the diagram of the shearing force on the action of the unit force in the direction in which we want to find the displacement and direction of the shearing forces. So I is indication of the direction. And in the denominator, we have the product of the area of transverse section of the element of mechanical system, and J is the elasticity modulus for the shearing. It is for the proportional elastic materials, usually the elasticity modulus for the transverse shearing stress is proportional in a definite dependence on the elasticity modulus for the material compression and stretch. So it's not subject to consider today, but actually we have to know about that. Remember, this is the area of the transverse section. Plus, so summand is the summand of a total of integrals of in the integrand we have the fraction, in the numerator we have the product of the ordinate of diagram of the longitudinal force of all of external load action on the mechanical system and multiplied by the diagram of longitudinal forces acting on in the mechanical system under influence of the unit force in the direction I, in which we want to find the displacement and action of the normal forces action on the mechanical system. And the denominator we have the product of the elasticity modulus E by the area of the transverse section of the rod. So we have three summands. Considering the assigned issue, any assigned issue, usually we can adopt just only one or maybe two summands, usually one. For the frames, for example, we adopted the first summand because the deformation and action of the bending moments for the frames are usually much bigger than deformation and the influence of shearing forces on normal forces. So the second summand would be important by its magnitude if we consider the deformation and the shearing forces of the element of the mechanical system, which weights at h in the extent of the mechanical system element in the direction in the section of corresponded with transverse force in transverse section. When the extent the length of this element of mechanical system is comparable with the length of the system element between the nodes. So if it is very wide, so actually, yeah, it would be correctly to say the width of the element of the mechanical system would be comparable with its length. Is wide, yes. So we have to consider as well the shearing forces influence on the displacement of the point of the element mechanical system, the mechanical system in the integral. And the last one is actual for the trusses, as we consider truss as connection of the beams connected by hinges. So these hinges do not transmit bending moments exactly, and we assume that we remember that bending moments are in the derivative interdependence with the shearing forces. So the bending moments would be zero. Usually the shearing forces is zero. Shearing forces are zero for the trusses mechanical parts as well. For the trusses disks, unchangeable mechanical parts of trusses is zeros. So they are under influence of the longitudinal forces. So we, for the trusses, can apply only last one summand. A little bit about the factor mu applied in the summand of the Mohr integral for the displacement and action of the transverse forces. The factor mu characterizes the influence of the distribution of the area of the transverse section of the element mechanical system in the direction perpendicular to the axis of the element bending. So if we consider the flat state and we consider bending moments scalar on plane, so the shearing forces as well scalar on plane. But shearing force we can consider on the plane as vector as well, but not so much important in this definite one case. But if on the plane, which is the axis 0y, lie in the axis is perpendicular to the plane of the consideration. So the shaded part of the transverse section of beam is we can consider just like the increment of the area, and we would consider for each definite one part. If we would like to find the distribution of the shearing stresses along the ordinate axis, we can use and the impact on the displacement adjection of the transverse forces. We can consider this formula. This formula equal to the first is a fraction of the area of this transverse section divided by the moment inertia of this section, geometric moment inertia of the area of this section relative abscissa axis crossing the center of the square of this transverse section, multiplied by integral by all this area of the integrand. Integrand is the fraction of the static moment, is a product of the area cut off part shaded here, and on the distance between the center of this area to the center of the area of the whole section, to the abscissa axis, as we consider abscissa axis, crosses the center of this area of the full section of this transverse section of element of mechanical system. So this static moment of this area cut out to relate with the abscissa axis or relate with the center of the area of the total section, we consider in the numerator squared in the power to the second degree, and divided by squared thickness of the element of mechanical system. Yeah, if we here consider the flight state and we consider the plane which in the axis y is in and the axis x is perpendicular, then the b is the thickness in the perpendicular, the size of the section in the perpendicular direction to the plane we consider the mechanical system in. Yeah, and this helps us to find the section shape factor for finding the displacement adjection of the transverse force. Actually, we can have a lot of the practical accommodation to find this factor for definite cases. It can be, in particular cases, for solid rectangular section, this coefficient is equal to relative to any of two axes. 6/5 fraction for solid circular section. This factor is fraction 10/9 for thin walled circular profile of the pipe. This factor could be 2, and etc. Yeah, I will not go into the deep to explain how it can be found, but it is the separate question considering the using the use of Mohr integral. And what is the sequence of determining the displacement of the mechanical system nodes using the Mohr integral? First, we have to determine the diagram of the specified load. We have to find the load diagram, so-called load diagram. Next, we have to determine the diagrams of unit forces. Actually, to be more correctly to say unit efforts, could be not only loads. If we need to find not translational displacement of definite one point in any direction, but we would like to find the pending displacement. So probably the not unit force, but it can be unit moment or unit shearing force or unit longitudinal force. Anyway, this is a unit effort applied to the direction of the moment of the. We have to find the bending moment, in which in the direction of the we want to find the displacement. Sorry, this could be a little mistake. The desired displacement, thought displacement. Next, we can use the GOT diagrams in the article in the point 1 and point item 1, item 2. We have diagrams, and we can find the use a Mohr integral formula, this one, to find the displacements of the in the options. of in the option of truss, perhaps truss is hingely connected elements of the mechanical system, disks, or could be a truss consisting of beams, rods, etc., connected by hinges. We can consider the longitudinal deformation of trusses, and we can use this formula of the Mohr integral, just only the last one summoned in the first equation. Or if we would like to find the displacement of frame. Frame is usually rigidly connection of the element mechanical system. So we would consider predominantly the product of diagrams of and the patterns of the exchange along the axis. We would like patterns diagrams. We would like to consider dependent. So in this case, we will have the Mohr integral as the first summand of the general equation of the Mohr integral, neglecting the second and third summand, etc. So let's please consider the example of definition of the displacement of the point C of the assigned frame indicated on the draft 3.7.2a. So statically definable embedded on the left hand point A frame consisting of two elements rigidly connected in the point B, and to the point C we have the applied force 9 kilonewton, and bending moment is 7 kilonewton by meter, and we have for the up one part of the frame the evenly distributed load 2 kilonewton per meter. So, and the sizes of this frame are the length is 4 meter and the h is 2 meter. So to use a more, and it is assigned to find the displacement of the point C of the loaded frame in the direction leftward. We assume that the unit of force applied to the point C, and the directed P force, unit force applied leftward. So we can go from the right point C to the left to B and to A. This is a little bit easier because we have not had to find the support action at the point. It's not a big difficulty. Yes, we can find and we can go from left to right. Not so much important, but we will go from right to left. If you would like to go to another way, so we first have to find the components of the reaction and the embedding A, and the support rotation moment in the embedding A. Okay, and we will indicate the elements of the system going from right to left as the first element, the second one rigidly connected in the point B and embedded in the point A, loaded by 3 efforts, like distributed force and concentrated force and bending moment. And we use the Mohr integral to find on the section from section 1, we consider the axis. Usually we are coincide axis. For the Mohr integral, we have to find the limits of the integration, the limit from 0 to the end of the element, from 0 to. So this limits of the integration adopted to each one definite element of mechanical system in the sequence of the consideration when finding the displacement by the Mohr integral. And the abscissa axis, any one coordinate axis, not so much important. X could be is the line from the beginning of the element to the end on the straight line going from 2 points, the beginning and the end of the element. So we say X axis. For the first one section, the vertical part of the mechanical system considered, first we have to have the diagram of the bending moment of the external load. And we can do that by the formula indicated here as the bending moment under the external load assigned F and the bending moment F. We have that this is the pattern of the change of the bending moments on in the vertical element of the mechanical system and action of the assigned load. And exactly, I have to remind that we do not use any other simplification of determination of, this is definitely one exercise. Don't use the simplification, we don't use Vereshchagin rule, we don't use the Simpson rule, we don't use the trapezoid rule, or any other rules of determination of the Mohr integral. So we just have to find this integral directly. So we need to find the formula of product of two diagrams. Each of diagram characterizes each of diagram with the external load and on the unit load and the direction in which we have to find the displacement. All these diagrams we have first to find as mathematic equation, as mathematic, and after that we have to substitute this into the integral and to find the magnitude of the integral, that is the displacement of the point C and the action in the sought direction and the action of the forces loaded this frame. So actually we have two diagrams of the bending moments. We assume that we have, but we will not have this like a figure or the draft. We will have these diagrams of the bending moments like the mathematical equations. So the first diagram here of the frame considered on the load of the bending moment and the transverse force here in the point C, we have as bending moment along the section 1 will be moment rotating this counterclockwise. We will adopt the counterclockwise direction of the rotation as positive, minus force rotating clockwise. We consider rotation of any point of this first element rotating by the assigned force or rotating by the assigned moment. Could be the point located here, extended for the distance x from the point C, extended from by the distance x from the point B, etc. for here. So equal to moment and the force rotated in the other direction than the moment rotates counterclockwise, the force rotates clockwise for any section of this vertical part of the mechanical system. And finally, we have the formula. This is the assigned moment minus the rotate in the other direction, minus 9 is the force, multiplied by x, the distance between the last point C to the varied point of the application of the force F. The diagram of bending moment and in this same first section under the influence of the unit force P, we adopt equal to 1 at the point C, and how much it influences the bending moment, this force, independence on the distance from the point C along the element of the mechanical system by the axis X coincided with this element from the beginning of the element. So we have that the bending moment and the influence of the unit force is minus X. So moment is the product of the force by the arm is X, the force is 1, so moment is minus X, rotating counterclockwise, so minus X. Excuse me, rotating clockwise, so we have negative sign, minus sign, rotating by the unit force here, rotating relative any point of the section by the variable X. Okay, next we consider the section 2. Section 2 is the horizontal part of the mechanical system. And this is limits of the integral is from 0 to 4 meters. For the first segment is from 0 to 2 meters. So each limits of the integral for Mohr integral, each limit begins from the beginning of the definite one considered element of the mechanical system. For the second one, from 0. For the first one, from 0 to the end of this element, 4 meter or 2 meter, appropriately. The diagram of bending moment of of external load in the second section is in the second element is determined as this moment by the rigid connection of two elements. This moment transmitted to the second rod of the mechanical system. The moment of the force external applied to the point C leftward we have here as applied force F multiplied by arm of 2 meters here, but the another one direction then the rotation moment, this moment of the force F as well transmitted to the next one arm, to the next one element of the mechanical system, sorry. And as well, the distributed force Q impacted on the increase of the bending moment magnitude by the pattern as fraction, the numerator, the distributed load Q, evenly distributed product by the distance from the right part of the horizontal element of the mechanical system to the left as we go from right to left, and squared divided by 2. We'll go to particular explanation of the definite one summoned. So, and yeah, this is easy to understand, considering that the distributed load is a derivative of the concentrated load on the left, on the end of the considered limit of the distribution of the distributed load, and the concentrated load is derivative of the shearing force. The shearing force is derivative of etc. So we go, the concentrated load is derivative of the bending moment, excuse me, because of that. So finally we have that after the substitute of the sizes of the mechanical system and the magnitudes of the distributed load and the moment and force, we have that the bending moment on the horizontal part of the mechanical system is -11 minus x squared. This is x squared is distribution of the bending moment and the action of the distributed force, and the -11 is a constant, is a final constant. If is -11, we substitute for the first one equation, instead of x we can substitute the size, vertical size of the mechanical system 2, so the moment on behalf of the force F applied to the point C leftward is -9. Moment in the point B will be -9, product by 2 is -18. 7 minus 18 is -11. -11 here, minus x squared. The diagram of the bending moment in the second section under the force under the unit force is a constant, so evenly distributed constant. Why? Due to this leg, this leg is parallel to action of the unit force, line of the action of unit force. So the unit force caused the bending moment in the point B by the arm 2. So unit force 1, the rotation moment is 2, equal to the arm BC, and along the second one element of the mechanical system, this bending moment does not change. Okay, and so we have all factors. We have to substitute in the numerator of the fraction in the under of the integrand for the Mohr integral, and after the substitute this all in the integrand Mohr, this is the total of the integrals for two intervals from 0 to 2. The first interval from 0 to 4 is the second integral, and after that, when we substitute all that, we can have the mathematical equations. We can derive the common factor out of the brackets here. The common factor is the fraction 1 divided to rigidity, characteristic elasticity, and the moment, the index of the moment of the inertia of the transverse section of the elements of the mechanical system. For the systems, we have the same section of the elements first and the second of the considered mechanical system. So they multiplied by the equations, results of finding these integrals 2 after the substitute of the limits of the integration and finding the integrals. And we can find that the displacement in the required direction, horizontal direction of the point C, leftward is 140.67 divided by the rigidity characteristic of the frame, of the transverse section of the frame. Exactly, we have to obey the dimensions as we have the international system of dimensions, which could be the elasticity, megapascal. Megapascal, this is meters in the power by 4, etc. After that, correct use of the dimensions of the used indexes, we can find this displacement probably in the system units, international C, or another system units, not so much important for this definite one consideration. Questions and comments. 3.7.1. Castellano theorem showing the dependence of displacement of points, application of forces, and the energy of deformation of the elastic body of these forces. Okay, so I did not talk a lot about the Castellano theorem, but the Castellano theorem is a theorem of the dependence of the deformations of the elastic proportional mechanical system in any direction under the action of the forces applied to another directions, maybe to the same and to another directions. This Castellano theorem is in the grounds of the Mohr integral, and for finding the displacement of the elastically proportional mechanical systems for the flat state, as we did consider for the considered example, or in the special state. Special we can consider for six displacements due to the 6 axes in the space. And using Mohr 3.7.2, using Mohr integral to find the displacement of any point of the in the direction of the applied unit force. For the flat state, we consider use a Mohr integral under the finding the displacement of the proportionally elastic mechanical system under action of the distributed load, bending moment, and concentrated force. And actually, we have 3 summands of Mohr integral. One summand is a displacement under action of the bending moment, and the second summand under action of the transverse forces, and the third one is the displacement of the mechanical system under action of the longitudinal forces. And sometimes, considering the properties of the system assigned, we can use only one summand. Maybe for the frames, it will be the first one summand, displacement of the mechanical system under action of the external load, considering the bending of the frame for any mechanical system or maybe frame. And the last one summand, we can the dependence of the displacement under external load for the mechanical system, considering the longitudinal forces in the elements of the mechanical system, we can consider by for the trusses, for hingedly connected disks, or maybe hingedly connected beams, if we consider the beams as disks, unchangeable elements, geometrically unchangeable elements of mechanical system, from the statically definable point of view. And sometimes we use the displacement under action of the shearing forces. This is for the mechanical systems which y is comparable with the length if we consider the flat state of the loading of the mechanical system. 3.7.3, finding the cross-section shape factor when determining the displacement under action of transverse force using Mohr integral. For one summand of the Mohr integral, the displacement of the elements of the points of the element mechanical system under action of the shearing forces, we count not only the diagrams of the action of the external load on the shearing forces, not diagram of the shearing forces and the action of the external load. And not only the diagram of the unit forces acting on the system, mechanical system, in the direction in which we have to find the displacement. But we have to account as well the so-called shape factor. Shape factor is a characteristic of the transverse section of the mechanical system under influence of the transverse force. And the shape factor depends on distribution of the material along the section, transverse section of the mechanical system element. And we can determine this like the proportion of the first element of this system, of the mathematical equation. Finding this shape factor is the fraction and the numerator is square area of the mechanical system section element. And the denominator we have the moment of the inertia and of the transverse section of the mechanical geometric moment of the inertia. And next, this fraction multiplied by integral. Integral is by the total area of transverse section of in the numerator of integral we have the moment of inertia of cut-off part of the transverse section area, and on the denominator we have the width of this, the thickness of the squared thickness of the the transverse section of the mechanical system, and then product by increment of the area of this shape. So this is the total integral of this integrand. Yeah, but this is just a particular question outside the Mohr integral use in general approach. 3.7.4, the sequence of determining of displacements of nodes of mechanical system using Mohr integral and multiplying diagram of forces, moment of forces. The sequence is first we have to do the diagram of the external load. Perhaps before that we have to find the support reaction, but sometimes if we have to find the definite point which is not the point of the support point displacement is zero. We don't consider the displacement of the support points of the mechanical systems. If for other point we can begin the finding of the displacement of the starting from this point to the support in the direction to the support, assuming that the displacement of support is zero. So the sequence in this definite one approach consists the following steps. So first, we have to do the diagram of the bending moments. If we consider the bending, maybe a diagram of the longitudinal forces, so shearing forces. Each is in what case we definite one case, what summons of the Mohr equation we're using. And second step, we have to determine the diagram and the action of the unit force in the likely direction in which we want to find the displacement and the action of the external load. It cannot be the diagram of the just a force, it can be diagram of the unit efforts. So for example, we have the assignment to find the displacement rotational of definite one point of the mechanical system. So this will be the unit bending moment. The unit force can be for finding the unit force diagram we consider when we find the displacement in the any translational direction. After the finding two diagrams and the action of the external load and of the bending moments and the action of the external load and the force, transverse or longitudinal, not so much important. That's different one case. We have to determine the mathematical equation of Mohr integral using the first, the last, or any other summand, or the middle summand under the action of the sharing forces, and to do the mathematical transforms with Mohr integral and to find the displacement. It can be the direct determination if we have mathematical equations for the bending moment diagram, or it can be the use of the approaches to find the Mohr integral when producing the diagrams in the numerator of the integrand of Mohr. So other ways we have is use the Vereshchagin rule, use the Simpson's rule, use trapezoid rule, etc. And we can use as well a direct product of the diagrams, having the mathematical equations for these diagrams. 3.7.5, determination Mohr integral by method of direct integration by multiplying diagrams forces in the given load unit force. Yeah, we had example of the direct determination of the Mohr integral with not the use of the any practical approaches like Simpson, Vereshchagin, trapezoid, etc. Thank you.